In this video, we're going to introduce reactions of organometallic compounds with ketones and aldehydes, drawing an analogy between complex metal hydride reductions and reactions of organometallic reagents with ketones and aldehydes. So first, let's revisit the reductions of ketones and aldehydes to alcohols using lithium aluminum hydride and sodium borohydride, these complex metal hydride reagents. Recall that the key to these reactions was nucleophilic addition of the hydride anion built into the metal hydride anion to the carbonyl carbon with cleavage of the pi bond and formation of an alkoxide intermediate. So I've left the intermediate out here, but the point I want to make is that this is a nucleophilic addition, or AD sub N elementary step. This is an example of nucleophilic addition to the carbonyl carbon. And after treatment with water to protonate that alkoxide intermediate, we end up with an alcohol in which a hydrogen has added to the carbonyl carbon and a hydrogen has added to the carbonyl oxygen. Now, something that we noted in general in an earlier video that's worth pointing out here is that reduction of a ketone or aldehyde can generate a stereocenter and convert an achiral starting material into a chiral product. So for example, 2-butanone, when it's treated with lithium aluminum hydride followed by aqueous workup, or sodium borohydride and methanol, we end up with a mixture of two stereoisomers derived from the hydride nucleophile adding above the plane of the carbonyl group or below the plane of the carbonyl group. And if we do the configurational label assignment here, we find that this stereocenter has the R configuration and this stereocenter has the S configuration. So these are enantiomers. And for example, if we're working a problem, we could draw one or the other of these enantiomers and just write plus En to indicate that the enantiomer is also formed. And these are formed in equal amounts because we started with an achiral starting material and we're ending with chiral products. Now let's consider what happens if we replace that metal hydrogen bond with a bond between metal and carbon. The resulting species is known as an organometallic species, or more broadly, an organometallic reagent or compound. Organometallic compounds contain at least one carbon-metal bond. Because metals are less electronegative than carbon, these bonds tend to be polarized toward carbon, making the carbon atom nucleophilic. Carbon in these reagents is nucleophilic for the exact same reason that hydrogen in a complex metal hydride is nucleophilic. It is more electronegative, hydrogen or carbon, than the metal that it's linked to. And so we can think about in organometallic compounds a resonance structure involving pushing the metal-carbon bonding electrons to carbon and landing a negative formal charge on the carbon connected to the metal. And in many highly reactive organometallic compounds, organolithiums, organomagnesiums, Grignard reagents, the metal is kind of a spectator. Where the business is really happening is in the nucleophilic, essentially carbanion built into these structures. That said, organometallic compounds do exist on a continuum because there are a wide variety of metals on the periodic table, ranging from the alkali metals, which are extremely electropositive, to the right-hand side of the transition metal series, where those metals are actually getting pretty electronegative, and the post-transition metals like zinc, which are even more electronegative. And so as we move the metal along this continuum, the metal-carbon bond goes from being highly ionic in the case of an organolithium to highly covalent in the case of an organocuprate. This is a class of reagents that we'll encounter later in the course. And of course, there are varying degrees in between. So you can see in these electron density maps that there is quite a bit of negative charge on the ethyl group here, and in the organocuprate, there's much less negative charge built into the ethyl group. It's much less reactive, more tolerant of Lewis acidic functional groups and Bronsted acidic functional groups and all that good stuff. So mostly we'll focus our attention on these highly reactive organometallic reagents, organolithiums and Grignard reagents. Although we may occasionally see organozincs and in particular organocuprates a little bit later, where that mild reactivity actually provides a big synthetic advantage. The two classes of organometallic reagents with the most practical importance are organolithiums and Grignard reagents. Organolithiums are pretty self-explanatory. These are compounds in which some organic group R is linked to a lithium atom through a bond that is more or less ionic, very, very ionic in character, meaning R has quite a bit of carbanion character. A Grignard reagent is an organomagnesium halide. So magnesium generally has a +2 charge. And so it's linked to an R group, which acts quite a bit like a carbanion, and an X group, a halogen, typically chlorine or bromine, that acts like Cl- or Br-. Grignard reagents are typically formed through the reaction of an organohalide with magnesium metal. So we take Rx and we simply treat it with magnesium metal, often in an ethereal solvent like THF or diethyl ether, and the result is the organomagnesium halide in that ethereal solution, and we can often add our electrophile directly to that solution of the Grignard reagent. Organolithiums can be prepared a few different ways. We can do something similar to what we did in the magnesium case and start with an organohalide and treat with lithium metal. We can deprotonate a hydrocarbon using a very strong base. Tert-butyl lithium is one of the strongest bases in all of organic chemistry, and this can deprotonate at a wide variety of, for example, sp2 and sp3 hybridized carbons, generating organolithiums at those carbons where negative charge is more stable than it is in the sp3 hybridized tert-butyl lithium. Now, the third method, which is very, very commonly applied in practice, involves lithium halogen exchange, the exchange of a lithium atom for a halogen atom through something we can envision as a kind of reduction process, converting an organohalide into an organolithium reagent via the exchange of lithium with another organolithium compound. So it's a kind of reduction, essentially, lithium halogen exchange. Once we've got these strongly nucleophilic reagents in hand, we can treat them with a wide variety of electrophiles, and the electrophile of interest for us now is the carbonyl group in ketones and aldehydes. Organolithiums and Grignard reagents add to ketones and aldehydes irreversibly, and after aqueous workup, we end up with these alcohol products. So this is highly analogous to these complex metal hydride reductions we've seen previously. It's just instead of adding hydrogen, we're adding this R2 group built into the organometallic reagent to the carbonyl compound. You do want to watch out for stereochemistry here, because this reaction converts a trigonal planar carbonyl carbon into a tetrahedral alcohol carbon, and that can create a stereocenter and introduce chirality where we only had achirality in the starting material. And so you want to watch out for the generation of enantiomers in this reaction. Now let's dig into the mechanism of the reaction a little bit, and we're going to draw again a deep analogy between complex metal hydride reductions and reactions of Grignard reagents and organolithiums. And here I'm using a Grignard reagent. The reaction mechanism for organolithiums is perfectly analogous, where we simply replace RMgX with the lithium, and the mechanism works exactly the same. So as we've just seen, this R2-Mg bond is highly polarized toward R2, making R2 behave like a carbanion. And so that R2-Mg bond can add to the carbonyl carbon, kicking electrons up to the carbonyl oxygen in an Ad sub n elementary step. The RMgX plus cation kind of floats away. It's essentially a spectator, and we end up with this alkoxide intermediate. We then add water to the reaction mixture, and that added water protonates the alkoxide. We use a large excess of water to drive this protonation all the way to the product alcohol, and the neutral product is an alcohol in which the R2 group is added to the carbonyl carbon, and a hydrogen, via a proton coming from water, has added to the carbonyl oxygen. And so, basic mechanism here, under basic conditions, we add the nucleophile first because it's a very, very strong nucleophile here, right? And then on workup, we protonate the alkoxide intermediate to get the neutral alcohol product.